So in topology of real numbers, I'll be discussing open sets with examples and theorems. So first of all, the definition: open set. Let A be a subset of R. R here is set of real numbers. A is said to be open set if it is neighborhood of each of its points. If it is neighborhood of each of its points. Neighborhood I have discussed in previous lecture. You can check the lecture of neighborhoods in Topology of Real Numbers playlist. So neighborhood is a set is a neighborhood of a point if open interval containing that point is contained in that set. X minus epsilon, x plus epsilon open interval should be subset of A if A is a neighborhood of X. So in terms of analysis, we can give this definition for an open set as A is open set for each element X which is belonging to that set. A is open set if for each X belongs to A, means we are talking about each and every element of the set. There exists epsilon positive such that the open interval containing X should be the subset of A. This definition of neighborhood should be satisfied for each and every element of set A, then A will be open. So we can also say that if A is not open, that means there exists at least one point of the set of which the set is not neighborhood. Means at least one point in the set will be like any open interval containing that point x minus epsilon, x plus epsilon, however small epsilon we take, however small interval we take, x minus epsilon, x plus epsilon interval containing point x will not be contained in A, so that A could not be the neighborhood of at least one point. That is why it might not be an open set. Examples of open sets: every open interval is neighborhood of each of its points. Every open interval A to B is neighborhood of each of its points. Therefore, every open interval is an open set. Because for open set, a set should be neighborhood of each of its points. Open interval is neighborhood of each of its points. We have discussed these examples in the definition of neighborhood lecture. Second is the red set of real number is neighborhood of each of its points. Whenever we choose any real number, the open interval containing that point lies in the real number set. Therefore, R is neighborhood of each of its points and hence open. The third is set of natural number is not an open set. Why? Because set of natural number is not neighborhood of any of its point. For example, if I take 1, open interval containing 1 contains more than, means many other elements which are not natural. So this in open interval is not contained in n. Hence n is not neighborhood of 1. But this was one of the example. We are talking about each and every element of n. So we will talk in general x belongs to n. Open interval is not contained in n. That is why n is not open. Some more examples on open sets. First of all, the empty set is an open set. Why? Because empty set is the set where there is no point in the set of which the set is not neighborhood. Since phi contains no element, so in the contrary definition we say there exists no point for which the phi is not neighborhood, hence phi has to be assumed as open set. Any semi-closed, semi-open interval is not an open set because this particular interval which I have taken is not neighborhood of A. The interval A to B, B closed is also not an open set because it is not neighborhood of B. The closed interval A to B is also not an open set because it is not neighborhood of A and B both. The set of integers Z is not an open set. Reason is same as set of natural number. It is not neighborhood of any of its point. The set of rational numbers is also not an open set. Why? Because for every x belonging to rational number, the open interval x minus epsilon x plus epsilon contains infinite many irrational number also. So this particular interval, open interval x minus epsilon x plus epsilon, cannot be contained in Q, set of rational. So it is not neighborhood of each of its points, hence it is not open. The set of finite collection of element is not an open set. Set of finite number of elements is not an open set. Or rather I should say a non-empty finite set is not open set, as it is not neighborhood of each of its points. Next we have theorems on open sets. The very first theorem is the union of two open sets is an open set. If we have two open sets, their union will also be an open set. So let A and B are two open sets. A and B are two open sets. We need to show A union B is also an open set. Let us consider X be an arbitrary element in A union B. We always prove the theorems for arbitrary elements, because arbitrary means randomly chosen. We have chosen just any element of the set and we have made it neighborhood of that element. Means any element I'll choose, the set will be the neighborhood of that. That means the set is neighborhood of each of its points. That is our main concern to prove. So since X belongs to union, it has to belong either of the set A or B. Also, as X belongs to A, if X belongs to A is an open set, A is neighborhood of X. And in the other case, when X belongs to B, B is also an open set. So in this case, B has to be the neighborhood of X. So in either of the criteria, we'll show union is a neighborhood of X. Because A is a subset of union A union B and B is also subset of A union B. And in neighborhood lecture, I have proved any superset of neighborhood of a point is also neighborhood of that particular point. A and B are open sets. A and B are neighborhood of X. So A union B being the superset of both has to be neighborhood of X. This simply means in both the cases A union B is neighborhood of X. But since X was arbitrarily chosen from set A union B and the set became neighborhood of X, this implies any element I'll choose in the set, it will become neighborhood of it. So A union B is neighborhood of each of its elements or each of its points. Hence A union B is an open set. This proves the result. For next result, the second theorem, the intersection of two open sets is an open set. Let A and B are two open sets. We need to prove A intersection B is also an open set. If A intersection B is empty, then there is nothing to prove as empty set is an open set. So by this A intersection B will be open. So we consider let it be non-empty, and it has some elements. Let X be any arbitrary element in the set. Theorem will always be proved for arbitrary element. You cannot take specific example. Now X belongs to A intersection B, and since A intersection B is a subset of A and B both, so whenever an element belonging to the set, it must be belonging in both the sets. X belongs to A and X belongs to B. And both A and B are open sets given to us. So they are neighborhood of each of their points. So that means A and B both are neighborhoods of X. Since both are neighborhoods of X, their intersection which contains the common points of them has to be neighborhood of X too. So this implies A intersection B is also neighborhood of X. But X was arbitrarily chosen from the set A intersection B, and A intersection B became neighborhood of X. That means it is neighborhood of each of its elements, and hence it is open. This proves the result. Next theorem is the union of an arbitrary family of open sets is an open set. Theorem 3. The union of an arbitrary family of open sets is an open set. For this, first you need to understand what is arbitrary family. Also, we have proved the union of two open set is also an open set. So this theorem is exactly similar to that concept, but here instead of two sets, it's a collection of arbitrary family. So one kind of family we have arbitrary family. This is A lambda. Lambda belongs to index set. This symbol is of index set. Another family is an finite family. Finite family is a sequential terms a1, a2, an. It goes like this: I running from 1 to n is a natural number. Means collection is fixed. You need to take 1 to n. And in arbitrary family, you have chosen randomly. Suppose I have taken the first element as a1, then second element I have taken as a20, then a27, a35, likewise, randomly selected. There is no sequence. So a lambda, lambda belongs to index set. Index will be here 1, 20, 27, means whichever index element you have chosen. So this is the criteria of representation of arbitrary family. Let A lambda collection, lambda belongs to index set, be an arbitrary family of open sets. And we need to prove the union of this collection is also an open set. Union of A lambda, lambda belongs to index set, is also an open set. So likewise we'll take arbitrary element. Let X belongs to X be any arbitrary element in this collection, the union collection. So X belongs to the union means X belongs to A lambda for at least one lambda belongs to index set. Means at least one set it should belong if it is coming to the union. And every A lambda is an open set. So every A lambda is a neighborhood of each of its point. It has to be neighborhood of X if X is belonging to any A lambda. And since every element of the collection A lambda is a subset of the union, so if A lambda is a neighborhood of X, union is a neighborhood of X. How? Because in neighborhood we have studied superset of neighborhood of a point is also a neighborhood of that point. So we have chosen a particular arbitrary, not particular, any arbitrary element in the collection, and the collection became the neighborhood of that element. That means neighborhood is collection is neighborhood of each of its points. Hence the collection of union arbitrary family is an open set. Next we have the intersection of finite family of open sets is open. Now in intersection we take finite family. So finite family I have already discussed how I will be choosing I is a natural number, 1 to n it will be running is a finite collection. And also we have proved the result for two sets already. So here is a collection A1, A2, An. I is a natural number, I running from 1 to n is a finite collection of open sets. We need to prove the intersection collection, intersection AI means A1 intersection A2 intersection An is also an open set. So like we have done this theorem that intersection of two open set is open, in a similar pattern we will be doing this. If intersection contains nothing, if intersection is empty, this is quite possible. Like it's a collection of n sets and it's quite possible that intersection contains nothing. If it is so, then there is nothing to prove, as empty set is an open set, which proves the result. So we consider this to be non-empty. It contains some elements. I am assuming an arbitrary element x belonging into the collection. Since x belongs to the intersection, it must belongs to each and every I running from 1 to n. And each AI is an open set. And each AI is an open set means each set I running from 1 to n is neighborhood of x. Because this is the definition of open set, it has to be neighborhood of each of its points. So means I'll be getting, for every set I'll be getting a different epsilon. See what we are doing. Suppose we need to say the open interval containing x must be the subset of AI. So we are considering for A1, suppose I am getting epsilon 1, for A2 I am getting epsilon 2, for A3 I am getting epsilon 3 interval, likewise. So if I need to prove that the interval containing x must belongs to the intersection, so I need to choose the minimum epsilon, so that the interval containing x with epsilon should be the subset of each and every AI. So here first of all I am choosing different epsilon. So I have written epsilon I running from 1 to n. X minus epsilon I, x plus epsilon I is a subset of AI for each I. And next we are taking minimum of these collection epsilon. This epsilon will be the subset of AI for every I. This means the interval is going in the intersection collection. Intersection, not every intersection of AI is neighborhood of x now. Why? Because interval containing x is a subset of intersection of AI. Because it is going in the every AI, so it must be going in the intersection AI. Since x was arbitrary element, so intersection AI is neighborhood of each of its points, and hence intersection is open set. So by this we have proved the result, intersection of finite collection of open sets is open. Next I will be discussing few questions, because with examples or questions the concept is more clear. So the question is, answer in yes or no. The first part, can a finite set be open? Can a finite set be open? Second part, Can a non-empty finite set be open? Third part, is every infinite set be open? So the answer of first part is yes. Phi is open. Phi is a finite set. Finite set and open set both. For second part, non-empty finite set is open. Yes, no. Like 1, 2, 3, if you take any finite collection, it won't be neighborhood of any of its points. Every infinite set is open. No. Set of rational number we have proved in example, which is not open, as is an infinite set. Next is question, give example of these. Give an example of first part, an open set which is not an interval. So example will be, choose union of any two open interval. Whenever we take union of two open interval, it is not interval. 1 to 2 union 3 to 4 is not an interval, but it is an open set. How it is an open set? Because we have studied union of two open sets is open. Second part, an interval which is not open. Here you can give semi-closed, semi-open interval example or closed interval example. Like 0 to 1 closed interval is not an open set. C part, a set which is neither an interval nor an open set.